The morning session, now we have Dr. Nikar Pradhan from Jackson State University, Jackson. I welcome you, Nikar Pradhan. Now I request Dr. Samir Ranjan Meher to introduce the speaker and start the proceedings.
Thank you, Dr. Cheralathan, and good morning to all. Good evening to Dr. Nihar Pradhan. Dr. Nihar Pradhan, Cheralathan, and good morning to all. Good evening to Dr. I think some other speaker is on. Dr. Nihar Pradhan, and good morning to all. Good evening. Yeah, so let me first introduce this speaker. Dr. Nihar Pradhan is currently working as an assistant professor in the Department of Physics at Jackson State University, Mississippi, USA. Dr. Nihar Pradhan obtained his PhD in physics from Worcester Polytechnic Institute, Massachusetts, USA. He also worked as a postdoctoral researcher at the National High Magnetic Field Laboratory, Tallahassee, Florida. His research interest mostly includes two-dimensional layered semiconductors for field effect transistor applications, insulator to metal transition on two-dimensional semiconductors, photovoltaic phototransistors, and novel optical effect on two-dimensional semiconductors, magnetic data storage, and spintronic-based devices on magnetic nanostructures. He has published more than 90 publications in reputed journals, which has got more than 2,000 citations, and he has been awarded 2 US patents also. So now the floor is yours, Dr. Nihar. So it's over to Dr. Nihar.
Thank you very much, organizer, and particularly Samir, that inviting me for this occasion. So let me share my screen. View full screen. Okay. Okay, can you see this screen?
Yes, we can see.
Okay. Thank you again for everyone to be here this morning in India. Today I will give you a glimpse of very current research topics. Okay, it's when you will see these results, probably these are, you should think that these are very preliminary research, okay, on these particular two-dimensional layered materials. And particularly I will talk about the heterostructure of all these many different types of van der Waals, particularly semiconducting materials. Here is the outlines. Generally, I will talk about the heterojunction photovoltaic solar cell based on these materials. But before that, if someone is new in this field, I will give you a little introduction about the 2D materials, basics of photovoltaic, particularly PN junction, that we will be using throughout the talks. And at the end, we will discuss about many different types of PN junctions, like lateral, vertical heterojunction, different types of contacts, and so on. And at the end, since this is the kind of a new field of photovoltaic application based on two-dimensional materials, so there are many challenges actually, okay? And all these are like a preliminary results. So you can guess like many challenges on these materials and many ideas you can get to improve, particularly if you are interested to work on these materials in not only the photovoltaic application, but anything like in optics. So let me give you a little introduction about these layer materials, how it looks like. If you look the structure or how the band gaps of these materials are. Here you can see that these are like a transition metal dichalcogenide is one of the category of these layer structure materials. Okay, and if you'll see that these we call TMDs. So TMDs or transition metal dichalcogenides are 3 atomic layer. We call this single atomic layer. Okay, or 1 layer materials. The middle one is the transition metal, and top and bottom, which is like a sandwich between 2 layers of chalcogen atoms. So they have very strong in plane covalent bonds. So if you will like single atomic layer materials, if you want to bend them, okay, then it won't break generally. So due to this covalent bond. But if you look the interaction between each layers, then they have weak van der Waals coupling. Because of weak coupling, you can actually separate them very easily by getting even a mechanical Scotch tape method from bulk material to single atomic layer materials. You can get it easily by mechanical exfoliation technique. So that's why, the weak coupling, sometimes it makes easier to make from bulk material to single atomic layer or few atomic layer of these materials. If you look the black phosphorus, another 2-dimensional materials, they looks like this in zigzag structure. And there are many other materials, but one of them is hexagonal boron nitride. You can see this is analogous to the graphene structure, hexagonal pattern of boron and nitrogen. So how these materials, particularly semiconducting layer materials, are so interesting. One of the interesting feature is tunable band gap as a function of number of layers. For example, if we take the MOS2 and if you look the bulk MOS2 band structure, then you can see that the band gap is 1.3 electron volt. Now, if we'll make thinner and thinner on these materials, then 4 atomic layer, 2 atomic layer, when you reach to single atomic layer, you can see that the band gap increases from 1.3 electron volt to 1.9 electron volt. And this phenomena, as we know that this is the quantum confinement effect, and you can think about if you took the quantum mechanics, simple quantum mechanics course, and if you did the particle in a box problem, then energy that we calculated is this, where L is the length of the box. Okay, now consider the length of the box, you can decrease, okay, smaller and smaller structure, then the energy will increase. So that's what it is happening, and that phenomena is called the quantum confinement effect. Another very interesting feature on these layer materials as a function of number of layers is like, the electron, when it goes from the conduction band, valence band to the conduction band, okay? If you look the bulk materials, you can see that the valence band, top of the valence band and bottom of the conduction band, they were not exactly top of each other. So this type of electron transition in bulk material is called as indirect band gap materials. So when the electron jumps from the valence band to the conduction band, okay, then it will go through many scattering process, lattice scattering and so on. So when it will jump again from the conduction band to valence band, it will release very less energy. Okay, so this process is governed by phonon scattering process. Okay, so we will get very, less energy. But when you look the single atomic layer of this material, the band structure is different. That you can see that the bottom of the conduction band and the top of the valence band, they were aligned perfectly on the top of each other. So in this case, if the electron is jumping from the conduction valence band to the conduction band, they can go directly up and they can release the same amount of energy to come to the valence band easily, and we can measure that energy. So single atomic layer materials, particularly in transition metal dichalcogenide, they have many applications in optoelectronic circuit because of this direct band gap nature. And if we look the photoluminescence, one of the quantity that you can measure, single atomic layer, this is the red line, which shows extremely high photoluminescence compared to just 2 atomic layer photoluminescence of the same material. So you can see that you can use, by using the single atomic layer of these materials, particularly transistor metal dichalcogenide, you can use this for many different applications, particularly LED. Okay, that's what we are looking for, the high light emission. So apart from this, I talk about the MOS2 for giving the example, but there are many 2-dimensional layer materials available today to explore electronics and optoelectronic properties. So here you can see some of them are listed here. Many of them are semiconductor, and some of them are insulator. For example, like a large band gap hexagonal boron nitride. Many of them are even metallic or semi-metallic, okay, like a graphene also. Some of the materials recently discovered. Few of them behaves like a superconductor, okay, at a low temperature. And recently there are some material also discovered in a single atomic layer form. They show the ferromagnetic nature. So if we manipulate the electronic, magnetic, and optical properties of these materials in a single atomic layer to few atomic layer, then there are many opportunities that we can use for future optoelectronic devices. So now if we look at today's market or even around your office, that how many electronics that we are using today? Probably there are very few electronics that we are using in our day-to-day life, because we do not have that kind of material to make or change all the materials around us, all the components around us with electronics. So particularly these 2-dimensional layer materials, okay, can fill many opportunities that which are not, probably we are not able to use silicon technology to replace these for the optoelectronic devices. So for example, here these 2-dimensional layer materials, when you make them single atomic layer to few atomic layer, they were transparent. Even like a 20 atomic layer, I will discuss about that. It shows like a transparent, completely transparent material. So you can use them transparent electronics, and these are flexible because of the strong covalent interaction between them along the layers. So you can actually make the flexible electronics, and we can actually grow them large area of these materials too, using different techniques. I will probably not discuss about the synthesis routes here, but there are many different techniques where you can use, grow them with large scale. So we can use actually large area electronics using these materials. Of course, since these are the flexible and transparent, you can use many flexible and transparent wearable electronic devices, as you can see here. So because of this planar geometry, these material, particularly semiconducting 2-dimensional materials, have large light matter interaction properties. If we look one of the example here, this is the calculated density of states of transistor metal dichalcogenide, and you can see some of them are here, MOS2, WS2, and tungsten diselenide. When you see the density of states calculation, you can see that very large spike feature, okay? And these large spike feature, which we call the Van Hoff singularities, and these are coming from the electronic density, which shows the electronic density of states, comes from the d orbital of the transistor metal and p orbital of the chalcogen atoms. Due to their wave function characteristics, okay, of these transistor metal dichalcogenides, as you can see, this spike-like feature which comes in Van Hoff singularities, that those are responsible for high or strong light matter interaction properties. And as you can see that when you shine the light, okay, you can easily generates many electron hole pairs because the materials can absorb so much light here, okay? But it is depend upon the number of layers. We'll discuss about that. But one of the example here, how strong this light matter interaction properties in this 2D semiconductor. So you can see here single atomic layer to few atomic layer of MOS2, which shows as a phototransistor or photodiode. Once you shine the light, it can generate the current, which is called the photocurrent. Okay, so if you will measure the photocurrent by shining the light, you can measure the responsivity here. The responsivity is the photo-generated current divided by incident optical power, and photo-generated current is the current with illuminated light. You can subtract the dark current. Dark current means without the illuminated light. So that ratio will give you the responsivity of these materials, how this material responds to the light. Okay, and you can see that from like even from ultraviolet to the infrared region, they show extremely high photoresponsivity, around like a 10 to the power 3 to like 10 ampere per watt. Okay, and this responsivity as a photodiode, which I'm talking about, these photodiodes responsivity is much higher than the current photodiode, which is the silicon photodiode or germanium photodiode that we are using today or available in the market. The photodiode, for example, the silicon photodiode that we are using today is around 0.5 ampere per watt responsivity. If you look at 530 nanometer or green laser, now if you compare that with just single atomic layer to few atomic layer of these materials, if you use as a photodiode, the responsivity is much higher, around like more than like 100 ampere per watt. Okay, so these materials shows, prove to be strong light matter interaction properties. They don't have only the strong light matter interaction properties, but they respond to the light very effectively, very quickly. Okay, here you can see that the light is up here, and you can measure the current as a function of time. When you shine the light, you can see within 10 microseconds. Okay, you can measure the light signal, the signal from the device, so it can quickly respond to the optical signal that it absorbs. So since these are like as we discussed about that, very strong covalent bonds, and they are flexible and transparent, you can bend them also without breaking them. Okay, and it can respond to the bending force. As you can see, there is 100 times that they this study shows it can bend up and down with 4 millimeter radius, and it can respond very quickly. So these materials have strong light matter interaction properties, as well as like any mechanical properties that we are looking for. So since we will be talking about the photovoltaic solar cell in this talk, I will go through little basics of the photovoltaic solar cell, particularly PN junction solar cell. So when you talk about the PN junction solar cell, we have two different kind of materials. Or if you look the silicon solar cell that we are using today, we have a N-type or N-doped silicon region, and we have a P-doped, which is the hole, okay, doped using the boron doped. Then when we put them together, okay, then it will form a PN junction, or N-type and P-type material. They combine together. So when you put them together, what will happen is, since N-type material has electron majority and P-type has the hole majority, some of the holes from P-type material, they will diffuse to the N-type, okay, N region. And some of the electron from the N-type material will diffuse to the P-type material. So in the junction, they will form a electric barrier. Okay, so there will be a positive layers coming from the positive charge layers coming from the P-type, and there will be the electrons or negative charge layers coming from the N-type materials, forms a electric field or potential barrier there. Now, after sometimes once you join together, it will reach to the equilibrium, looks like this. So now if we will apply the voltage using external battery, for example, as shown here, then what will happen is, let's consider you put the battery here and negative terminal is connected with the n-type object, okay, n-type material, so where the electrons are the majority charge carrier, and positive terminal is connected to the p-type material where holes are the majority charge carrier. Then what will happen is, since this is the positive connected with the positive charge, they will push away, okay, from this terminal where you connected. So they will push towards the junction here. Similarly, the electron, since connected to the electron negative charge, the electron will push from the terminal here towards the junction. So what will happen is, this junction region, that's the electric field region, they will be smaller and smaller because of the holes is coming this side, and also the electron is pushing towards the p side. So this junction will be narrow and narrow, and after some voltage, what will happen is, the electron will diffuse to the p side and the holes will diffuse to the n side, and they will flow through the external circuit. And that's what you will see, that in this case, after a certain voltage, the current will exponentially increasing. Okay, so this is called forward bias of the PN junction. Now, in other hand, if we will reverse this battery, okay, positive and negative terminal as shown here, positive terminal connected with the n side where electrons are there, negative terminal connected to the p side where holes are there. Then what will happen is, this negative terminal, the holes will be sucked with this negative terminal, okay, and the electrons will also attracted to the positive terminal. Then what will happen to the junction? This junction will be it will grow now larger and larger, long, okay, the length of the junction will be more now. So what will happen? There is no charge diffusion, okay, no more electron is going through the whole side, or no more holes is going through the n-type region or electron side. So this region is more resistive now. Okay, so you can see since the resistance of this path or the junction increases, there is no current will pass through the circuit. So you will see that this part is called as reverse bias. So in the reverse bias, in this case, there is no current. Okay, so that's why the current is flat here. You can see the red line. Now, what will happen? You are in the forward bias. Let's stay there. And if we'll apply, or if we'll shine the optical power, okay, the photon will absorb on these materials. The photon will absorb throughout the N and P type materials. But what will happen in junction is, there are already electrons and holes are there. Okay, there is a built-in electric field. So when you shine the light onto this junction, there will be many free electron and hole pairs it will generate by absorbing the photon. So all those electrons and hole pairs which will generate by absorbing this photon, electron will move in one side, hole will move in other side. If we'll just connect the with the wire outside the terminal without applying any voltage, okay, those free electrons and holes will flow through the outside circuit, and that will generate the electricity. And this is the basic idea of the PN junction solar cell. And in that case, once you shine the light, you will see that there will be a lot of current you will be using here. Okay, at 0 voltage, you will see the current. Okay, that's the region we call the short circuit current, and the current will pass through the voltage axis. Okay, at some point where the current will be 0, that is called the open circuit voltage, and this window will provide you the power, photovoltaic power, or we calculate the efficiency. We'll discuss about that. And this is the basic principle of the photovoltaic solar cell we'll be using here in 2-dimensional material. But before going to the photovoltaic solar cell based on these 2D materials, I will discuss about this field effect transistor because we will be using the same mechanism on this material. So field effect transistor are the 3-terminal device. One is the drain, another is the source, where you can apply the drain source voltage to move the charge carrier from source to drain. Okay, that's what you are measuring. And the third terminal is called the gate. Okay, you can apply the back gate voltage underneath, which is separated by the dielectric material, or you can apply the top gate if you will encapsulate the device using top dielectric material. So the gate voltage, when you apply that, it will accumulate the charges that you need or the materials has, okay? And those charge carriers will move when you apply the drain source voltage. That's what you, so gate voltage generally works as a control of charge carrier that will pass through this channel or through this semiconducting, transistor. Now, how this N-type, P-type, or ambipolar field effect transistor looks like. So this is the, again, the transistor, how it looks like, source and drain, and let's say this is the back gate. So if you apply the negative gate voltage, since this is the capacitor, okay, it is the gate dielectric, you apply the gate voltage with respect to source. So if you apply the negative gate voltage, electron will be here because it is negative terminal. Then the opposite side of the capacitor, generally on the channel, you will accumulate the holes because of the capacitor. Okay, so if you apply the source and drain, the holes will move through the channel. That's what you can measure. So more and more negative voltage you apply, more and more holes will accumulate, and you can measure the more and more current. And that's what the P-type, or P-type means hole dominated field effect transistor looks like. So at negative gate voltage, your transistor is on. At positive gate voltage, since there is no, no electron here, if there is no electron, okay, then the transistor will be switched off. This is the typical P-type field effect transistor looks like. Now, if your material, for example, does not have holes, but it has electron, okay, then you need to apply the voltage, gate voltage in positive sides. Then the you can accumulate the electron here, and the field effect transistor will look just opposite to the P-type, okay? And this is called typical N-type field effect transistor. Now, some of the material we'll discuss here, they were not only they don't have only the electrons, but they have also holes. Electrons and holes both are present. So in that case, if you sweep the gate voltage from negative to positive, then you will see the P-type field effect transistor as well as N-type field effect transistor here, okay? So both the N and P-type transistor curve you can see, and this materials has a lot of application from the MOSFET to many other applications we'll discuss about, and we call it ambipolar field effect transistor. So here is the example, the MOS2, for example, this is the MOS2. You can see that the typical MOS2, single atomic layer MOS2 field effect transistor. When you apply the positive gate voltage, the transistor is on. So this is called typical N-type field effect transistor in MOS2. Now, if we look the tungsten diselenide field effect transistor here, you can see 2 atomic layer of tungsten diselenide field effect transistor. This shows that if you apply the negative gate voltage, transistor is switching on, okay? In positive gate voltage, there is no current. So this shows that WSC2 is P-type field effect transistor. But we also, synthesize similar way MOSC2 and RESC2, and this shows that you can see that if you sweep negative to positive gate voltage, you see P-type field effect transistor as well as N-type field effect transistor, okay, in both MOSC2 and RESC2. And these are actually, they have tremendous application in optoelectronics that we will discuss in photovoltaic solar cell. And all these materials, you can see that the mobility value actually you can calculate from this transistor graph will tell you that how fast the charge carrier, whether it is electron or the holes, okay, they were moving inside the material. So larger the mobility is good for the electronics application. And you can see that these are 200 to 300 centimeters square per volt second, the mobility that you can calculate from just single atomic layer to maybe 10 atomic layer of these devices. So let's go now to the photovoltaic solar cell. We know now these materials are, it behaves like a N-type, it behaves like a P-type also, and some of these 2D materials can behave like a ambipolar, where both electrons and holes are there, okay? So we'll discuss about the photovoltaic effect based on these materials using even Schottky barrier, okay? If you will use a different metal contact on a single two-dimensional materials, okay? For example, palladium and here gold, then because of the Schottky barrier height difference between the source and the drain, you can actually form the PN junction, and that will provide you the photovoltaic solar cell. So another one, if you have a single materials, okay, just one type of material, for example, MOSC2 is the ambipolar. So how you can create just electron doped in half of these materials, and half of the other part of the channel you create or doped with holes. In that case, if you able to create the dope half of the channel with electron and half of the channel with holes, then you will have the PN junction, which will be the lateral PN junction. We'll discuss about that. And some of the materials actually you can create or synthesize as the N and P type, okay, in lateral PN junction. And we'll also discuss about the vertical PN junction. If you have a N-type material and another is P-type material, you put together top of each other, okay? And that will work as the vertical PN junction solar cell. So let's discuss one by one together. So in this case, you see that this is the Schottky contact based photovoltaic effect, okay? So what they did is, this is the, you see the MOS2 materials, okay? And they use the gold as one of the contact, and palladium, there are two contacts. So using the gold and palladium and measure the photovoltaic effect between this gold and palladium, what they did is they can actually tune the bands, okay? The way the bands which work in using the gold and palladium, they behave completely different, okay? When you apply or apply the gate voltage in one direction, positive, so you can actually bend the bands in such a way that electron or one side, or maybe electron will flow, okay, hole will not. Then if we will apply the gate voltage in other side, then what will happen? The bands, you can tune them or bend them in opposite way. So the according to this band gap band tuning model, the holes will pass, okay? Holes will be the major charge carrier in this material. So because of the Schottky barrier between the palladium and the MOS2 and the gold and the MOS2, they have completely different, the Schottky barrier height they will make because of the materials different. So you will see that applying the gate voltage and drain source voltage, you will able to see a nice PN junction, okay? You can, nice PN junction, that means you can see the P type here and you can see here hole type. So P type, this is the N-type field effect transistor using gold and gold. This is the palladium when they use, it shows P type from just MOS2. Now using this technique, this is called the Schottky contact based photovoltaic solar cell. Now, using this technique, when you will see a rectification of current, because only one way it will favor, the current will pass or the carrier will pass because of the Schottky barrier height difference between the palladium contact and the gold contact. So it will show you a rectification like, or that is called the diode type or PN junction that we discussed soon, okay, just before. that kind of effect you will see in IV curve when you shine the optical signal with using a laser here, then you can see that you will get a photovoltaic effect. But this photovoltaic effect and the efficiency they measure actually, which is very low, maybe around 1 to 2 the photovoltaic efficiency that they got from this few atomic layer of MOSI2 phototransistor. But one thing here I would like to mention is, if someone is working here, the contacts, even though these are the Schottky contacts, these contacts can behave many different ways. If we'll make this photovoltaic cell on single atomic layer, or if we'll make this MOS2 10 atomic layer. So these Schottky contacts will be different. They are the barrier height will be completely different in terms of single atomic layer to few atomic layer. So you need to optimize, optimize the contact based on the number of layers of 2D materials to get the photovoltaic efficiency higher. So you have to play with many, different contacts with different number of layers of MOS2 and other materials. Okay, so let's move to the another. So here we discuss the contact effect. Now, if we have a semiconductor, let's consider it has like an ambipolar effect, both electrons and holes are there. So in this case, you see the MOSI2, and MOSI2 transistor shows p-type field effect transistor as well as n-type field effect transistor. So both electrons and hole, or we can say that intrinsic, these materials behaves like intrinsic. If we look the, the band diagrams, probably the Fermi level will be exactly or very close to the center or at the middle of the gap in this case. And if we look the charge carrier mobility at room temperature, both electron and holes have same amount of mobility, which is 100 centimeters square per volt second. So these are the perfect ambipolar field effect transistor. So how you can make the PN junction if you use the ambipolar two-dimensional material? So here is the device, and this is called electrostatically induced PN junction photovoltaic effect on these materials. So you will see that this is the MOS2, this is the source and drain. Underneath, this is the gate, which is the few atomic layer of hexagonal boron nitride. We put that underneath. You see that this is the split gate. This is the gold 1 gate, which is the gate 2, and this is the another gate called gate 1. This is called back gate since it is underneath. So now this between gate 1 and gate 2, there are probably 300 to 400 nanometer difference. So we are trying to make the junction region very sharp. So now when you apply the gate voltage, in this case positive or negative, let's say positive case, then you can accumulate the electron here. If you apply the gate voltage negative here, you can accumulate the holes here. Then you can form, actually by applying the different gate voltage positive and negative, you accumulate positive charge and negative charge. They were very close to each other, like 300 nanometer apart. So this is like act like a sharp PN junction. Now if we will just measure the current, you can see that the PN junction, these are the gate voltage different polarity. In one polarity, you can see nice rectification of current, diode like rectification, and in other way, if you reverse the gate voltage positive and negative, the rectification of current just it will change. So this is called PN diode and this is called NP diode. In any one you can get actually photovoltaic effect, and these are the actually the red lines are the theoretical fit where you can get the rectification parameter N, and this shows that the diode rectification N value is close to 1, which shows like ideal diode type of characteristic. And there are many different, actually you can apply the gate voltage in negative and positive with drain source voltage positive or negative. So you can have like a 4 different configuration of diode, PN, N and PP and NP, depends upon what type of polarity of the gate voltage that you are using to you are going to use, positive or positive negative combination. So you will have like a 4 different combination. So this is how the actual device looks like, or this is like around 10 to 12 atomic layer thick, okay, MOC2. You can see that, and it looks like transparent. Okay, if we put that on glass slide, it is completely transparent materials, even the 20 atomic layer of MOC2. So, and you can see that this is the SEM image. Now, in this case, if you shine the light, what will happen is you already form the PN junction. You have so many carrier, electron and holes, they form the sharp PN junction. Once you shine the light here on the junction, then it will generate huge amount of electrons and holes as free charge carrier. Electrons will flow in other way and holes will flow in other direction. It will connect, okay, the external circuit, and that will provide you the photovoltaic solar cell. So this is just a single material. Electrostatically, you are inducing N-type and P-type region that will give you the photovoltaic solar cell. And you can see that this is just the 10 to 12 atomic layer materials, and we calculated the photovoltaic efficiency here. I will show you 14%. Okay, so it is a transparent, flexible, few atomic layer materials. The efficiency that you will get is 14%, which is pretty close to like a silicon solar cell, which is 15 to 20% that we are using today. Okay, but again, I would like to remind you that the contacts that we use here, okay, we didn't play with the contact engineering. Okay, so you need to actually make sure that contacts are good. Okay, so even though they have the Schottky barrier height between the semiconductor and the metals, they were probably not ohmic type. Okay, there is a Schottky barrier height. You can try to eliminate using different technique, using the contact engineering. Then this efficiency might go up. And you can also play with thicker material or thinner material, and many different other techniques we'll discuss about later of this talk. So now let's look this single atomic layer, this electrostatic PN junction, how it looks like. Those are the 10 to 12 atomic layer. We got like a 14%, which is amazing. So if we look the single atomic layer here, tungsten diselenide, which is another material, such ambipolar behavior according to this study. And you can see that this split gate, 2 gates, okay? And it's, the cathode and anode, or the source and drain contacts, and you will get the photovoltaic effect, okay, using the same technique. But since this is the single atomic layer material, the absorption of photons or sunlight is poor, okay, compared to few atomic layers or multi-layers devices, as we discussed before in MOC2. So the efficiency of this, yes.
Yeah, you are having 5 more minutes.
All right, okay, I will just go ahead quickly. Yes, so the efficiency is like around less than 0.6%. So if we look, there are actually many different other way you can synthesize the PN junction photovoltaic solar cell. You can even, like when you synthesize in CVD technique, you could use the tungsten diselenide you can grow, then MOC2 you can grow, and alternatively, if you will grow one after another, you can stitch them together, okay? But the CVD technique, as far my knowledge and based on the research, they don't give, the good quality of the materials. So the photovoltaic efficiency that you will get, this is the PN junction behavior. But the photovoltaic efficiency you will get is very, very poor. But there is a way, there is, a lot of interest that you can use to go through these to form the large area PN junction devices. So this is another which I want to show you, is like a vertical PN junction. In this case, tungsten diselenide and MOS2, they were opposite, top of each other, okay? Overlapping region will form the PN junction in this case, because tungsten diselenide is P type and MOS2 is N type. But when you collect the charge carrier, electron and holes, they were laterally. So the junction is vertical, but you collect the electron and hole laterally. And in this case, this is the single atomic layer of MOS2 and WSC2 heterojunction solar cell, and which gives you the, less than 0.5% efficiency. So another type of how you can improve this vertical PN junction solar cell efficiency. One way is the contact engineering, as we discussed before. Here you can see the MOS2 and WSC2, okay, single atomic layer. This is the vertical PN junction, but what they did is they put the graphene on the top and the bottom also. So graphene actually makes the best ohmic contact on these materials, okay? So using this graphene, and they also cover whole area, whole junction area. So there are so many actually electron and hole pairs when it generates, you can actually collect many of them, okay? Without losing in different scattering, inside the material scattering mechanism. So according to this study, what will happen, what happened is, in compared to single atomic layer tungsten diselenide and MOS2, if you use the multi-layer, then this material multi-layer absorbs 35% higher compared to the single atomic layer of this PN junction. So using this graphene as a contact, actually you can collect actually much more electron and hole pairs because of the ohmic nature of the graphene contact on the 2D semiconductor materials. So this is another example of vertical PN junction, and you can see that you can actually produce large scale fabrication of the devices, okay, even with mechanical exfoliation technique. This is one of the example, or also there is called liquid phase exfoliation technique from the bulk material, and you can make the vertical heterojunction. But they treated, actually one thing here they did is they used the single MOS2 material. In MOS2 material, half of the, few atomic layer of the MOS2, bottom MOS2, treated with plasma treated, so they doped, okay, with P-type dopant, and the other, the top MOS2 was untreated, so it is N-type, and they form the PN heterojunction. In this case, they are able to get the this is just few atomic layer, not the single atomic layer material, and the efficiency they obtain is 2.8%. So there is, but in all the cases, actually, the contacts are not optimized in this case too, okay? So the contact engineering is one of the, the technique that in all the experiment that we discussed, no one has, except the graphene contact, okay? No one has studied that. So there are actually a lot of challenges, okay, in this photovoltaic application, particularly when, if you are interested in 2D materials-based photovoltaic devices. So one thing is they suffer like many different types of scattering, okay, inside the materials. So most of the photo conversion efficiency are lower in this case. Even though like electron hole pairs are generated, we cannot measure, maximum amount of electron and hole pairs that are generated by the source and drain contacts, because the contacts are Schottky and there is a huge Schottky barrier heights, okay? So it needs to be contact engineering, okay, which contacts will work the best, okay, that will improve the photovoltaic efficiency. So considering this fact, actually, you can actually try many different things. One of the things is the contact engineering that we discussed, where the Schottky contact, depending upon the how your the 2D materials based photovoltaic solar cell that you are making, make sure that the contacts are ohmic, okay? If you are, because the Schottky contacts will not provide you highest photovoltaic efficiency. So if we make the vertical PN junction, the contacts should be ohmic. Like one of the method is using the graphene contact, or other metallic or semi-metal 2D contacts would be the good idea. And low contact resistance. So this is needed because to collect the most of the charge charge carriers created by optical absorption, if the contact resistance is huge, again, it is the Schottky barrier and the contact resistance. If the contact resistance is low, most of the electron that will, electron and hole pair that will generate, you may able to, catch them or collect them in your cathode and electrons, that will increase your efficiency. And another thing is using the vertical heterostructure. Okay, in this case, if in this vertical heterostructure, you cover the source and drain contact in whole area. So you are actually collecting most of the electron and hole pair that it forms, because of the whole area is connected with the source and drain. But in this case, electron and hole pair, when it is, yes.
Sorry, actually you are running short of time.
Okay, I think I will go for the, this is the last slide, okay?
Okay.
This is, so what are the other technique that you can use to enhance the photovoltaic efficiency? Another way is you can stack many materials with a different band gap, as shown here. So these are the many different 2D materials with several different band gaps. So the optical absorption will increase, okay? And that will increase the efficiency. Another way is the plasmonic enhancement. If you will use the metal nanoparticle on the top of these 2D materials, the plasmons will actually collect or absorb the sunlight and then release the electron hole pair much more than just the single or few atomic layer, just bare 2D material. That will increase, as you can see here, okay? That will increase the photovoltaic efficiency. And this is the another, which is kind of a very exciting thing, that you can use some of the chemistry, okay? This is one of the chemicals called TFSI. When they use just the probably on the top of a single atomic layer of MOS2, the photoluminescence or the quantum yield, okay, they increase like a 200 times than the single atomic layer bare material. So these are all these things, if you can use together, then probably there is huge amount of like a photovoltaic efficiency that you can increase more efficiently using this 2D material. So I will stop here since the time is running out, and probably this is my last slide too.
Okay, thank you, Dr. Nihar. Actually, we are really running short of time. This was a very informative talk on 2D materials and their use in the electronic devices. And actually, there are plenty of queries and questions are there. So due to shortage of time, I can take hardly 1 or 2 queries, and rest I'll give your email ID to the participants so they can contact you through email and they can get clarified.
Absolutely.
So, okay, so one of the questions is all the FETs are that you showed, they are being operated at very high voltage. So is there any research going on in reducing the operational voltage?
Okay, so no, the FETs which I saw you, those are fabricated on 285 nanometer silicon dioxide gate. Okay, dielectric. So if we use the HBN, just the 10 nanometer, the operating voltage is just 1 to 2 volts. Okay, it is because of the thickness of the dielectric that we are using. This is the silicon dielectric. We use the back gate. You can use also top gate. Okay, aluminum oxide or hafnium oxide. This will operate within just 1 to 2 volt, as you saw, exactly same way.
Yeah, is there any role of anion vacancy in these 2D materials? Can we create any anion vacancy and that will impact the efficiency of the cells?
There are, few, you can create, the MOS2, for example, okay, it has already the MO, the electron, MO vacancy, okay. That's why MOS2 shows as N type, okay. the sulfur vacancy. That's why the MOS2 shows as N type. It is natural actually. So there are many other materials also. It shows the P type because of the vacancy of the sulfur or the metal transition metals. So what people do is for the MOS2, if it is just naturally it is occurring the sulfur vacancy, they used to make the P type by doping itself. Okay, so you can dope and change the polarity, but you can also use some of the other technique, probably irradiation technique, to bombard them the materials and make the vacancy. Yeah, there are, I think, several ways to do that.
Okay. Okay. So due to shortage of time, actually there are plenty of queries. So we'll ask the participants to mail you the queries.
Yeah.
Thank you, Dr. Nihar. So now it is over to the convener and the organizing secretary.
Thank you, Dr. Nigar. It was an excellent presentation. On behalf of organizing committee, I sincerely thank you for joining us. Thank you so much.
Thank you very much.
Our next speaker is waiting. Is Dr. Senthil Kumar from Korea Advanced Institute of Science and Technology, Republic of Korea. I request Dr. Anand Prabu to take over.
Thank you, Dr. Cheralathan. I welcome Professor. Hello, can you hear me?
Yes, yes, you're audible. Thank you.
Okay, so Dr. Anand, very much for your invitation. Am I allowed to proceed, or is there any introduction before?
Yes, kindly wait, sir. Kindly wait. Yes.
Yeah. Yeah. Can you hear me?
Yes.
Can you hear me? Yeah. Okay. So let me introduce you to the audience first. So I welcome. Just a moment. Here, how the click the. Okay, it's clear. Okay. I welcome Dr. Selvam to the conference, and he's the associate professor in Department of Material Science and Engineering, KAIST, Republic of Korea. For the past 20 years, he is in active research since getting his PhD in Material Science and Engineering, Advanced Institute of Science and Technology, Korea. And he continues PhD with a postdoc in EPFL laws in Switzerland, and then continued as a project leader in Samsung Advanced Institute of Technology, Korea for 7 years, and then moved on to the US as scientist with tenure in Material Science Division, Oregon National Laboratory from 2007 to 2017. So at the time I know him, started to know him, and then he moved on to KAIST as associate professor from 2017 to present time. Reading out his awards and honors, he got Frontier Award from Samsung Advanced Institute of Technology, and he was a senior fellow in Northwestern Oregon Institute of Science and Technology, USA for 2 years, and also received the Young Investigator Outstanding Achievement Award in the International Symposium on Integrated Ferroelectrics, and he also received the Frontier Scientist Award from the Korean Academy of Science and Technology. His publications is 148, which is an H index of 34, and book chapters of 5 and patent 79, which is the hallmark of top Korean researchers. They'll be focusing more on patents. So the title of his today's talk will be in materials imaging based design of piezoelectric sensors and energy harvesters. It is I'm more interested in this field also, because like we develop piezoelectric materials and we do the IR, XRD characterization, we do the sensor measurements in electrical case. But Professor talk is going to focus on materials imaging based technique. Just from the image, Professor is going to focus how can we distinguish the sensors and energy harvesters. So I welcome Professor once again to start his talk. Please, you can start your talk, Professor. You can share your screen.
Okay, let's see. Let's see if this works. Let's see. Do you see my screen? Oops. Do you see my screen? No, I don't think so. Okay. Let's see.
No, I can see the screen. Okay.
Oh, really?
I can see half screen now. Earlier, yeah, now it's okay. But
Oh,
it's okay for me now. Mother side only.
Let me try again. So do you see my screen right now?
Your mic is off.
Yes, we are able to see.
You can see my screen, right?
Yeah, yeah.
Okay, good. Thank you very much, Dr. Anand Prabu. It's my great pleasure and honor to present my research to all fellows here. And I'd like to share my recent findings on sensors and energy harvesters that we have made and analyzed. In addition, I'd like to introduce our grand vision of materials imaging-based approach to design functional materials and devices. So let me first begin with some soft introduction. So this is my lab. You can see the cherry blossom behind us. And you can also recognize one Indian female student. She's from IIT Kharagpur. Her name is Aditi Saha. And you can see we pursue diversity in our lab members. And on the right side of the picture, you will see interesting symbol where this is a partial derivative of something, integration of some molecular structure over the volume, which is again being differentiated with respect to either space or time. So this explains our basic philosophy. So we think the materials can be integrated at atomic scale with atomic precision, which will give us the whole part of our materials, but at the same time, to understand what happens at the structural level and how the structure properly relates, we need to tear them up, tear down respect to volume and time and energy and momentum. So that's what our materials imaging does. It's not just seeing the surface morphology, whether it's rough or smooth. It is really both structural and property imaging at multi-scale. So that's what our labs are founded on. Now, the presentation will be based on two talented students. Now, one of them has joined Samsung Electronics, as I have worked before, and the other student is has done a lot of wonderful job, but because of his health issue, he has decided to leave for a moment, but he will, I think, come back to join us in the near future. So Dr. Chongjae Ryu and
sorry to interrupt you. We will let this slide freeze there. The screen is actually looking very small because you are using dual screen, I guess.
Okay, so let me then try to see if I can do something else. I mean,
In
let me
single
show
screen.
my full screen.
Yeah.
And
yeah, it is dual screen, so you can go for one screen.
Now
it's very small actually. The screen size. Yeah.
Okay, then let me do this, the plan B. So I'm going to do this. Just in this kind of thing. Can you see me?
Yeah, I can see the student's name.
Yeah.
Those two names.
This is better, right?
Yeah, a little.
Okay.
Yeah. Little bigger. Little bigger.
Okay. Still small?
No, it's a little bigger. Can you make little bigger? Yeah.
Okay. So another promotional slide is that I am organizing IEEE IFCS ISAF 2020. So those who are interested in this is also a virtual conference, and now we are receiving all the registration, and it's highly related to this theme of this conference here. So please go and visit this website.
Okay. Yeah.
One thing that I told you was materials imaging and integration. The bigger grand vision we have is materials and molecular modeling, which has 3 M's, imaging, informatics, and integration, which has 3 I's. And this has been selected as one of the 10 flagship research areas in KAIST, aiming for 2031. So that's a Vision 50, which was reported in Future Report KAIST, and this is the only one related to material science. And if you see the next page, this month in Nature, we had Nature advertorial to show our own logo of materials integration and materials imaging, as well as the introduction to our M3I3 vision, where in the next slide, I will just simply tell you what it is. It's really doing reverse engineering from the property of interest down to structure that can realize that property, down to the processing recipe that can also realize the structure. So we are importing the conventional, the traditional material science and engineering pillars in a way that could be used with in conjunction with machine learning to expedite the material science and engineering in the
Professor,
future.
Professor,
Yes.
sorry. Actually, some participants are saying that PPT is not clear. They're not able to read the text. So what we go is some backwards, we can go the plan. In the stream, you can make a duplicate stream so that both the screen are showing the same PPT. And
I
that
got
you
it.
can make it full screen. Yeah.
Okay, let me do that. So duplicate. Okay. So where do I do that?
That window icon and the P. In the keyboard, there is a Windows icon on the left of the space bar, of the space bar, and then simultaneously press P.
Press B. You mean
P. Penny. Yeah. PENNY, penny, like that.
Can you spell out in your chat box? I don't think
yeah, I can say P.
P.
Yeah, that the window icon and the P simultaneously.
Okay.
You can see the screen choice also.
And then what do I do? Copy.
Duplicate.
Okay.
Yes.
I did it. Can you see it?
You can share the screen now. Share the PPT.
Let me do that. Can you see it?
Almost there. And now can we full screen?
Full screen.
Yeah.
You mean the
PowerPoint full screen. Presentation full screen.
Okay. Like this?
Not yet. It is there, but looking a little small actually, because the previous presentations and all, you can see the full screen of it, and also it is little hazy. The font size is a little hazy.
How about
now? If you can minimize the left-hand side, it will be fine. Left-hand side, this is fine now, I think.
This is fine.
But
oops.
Is it okay?
This is okay.
Please proceed, Professor, but probably if some participants are messaging the PPT is not clear, I'll just come back, interfere one more time, if at all, because clarity is also important here for the participants. You carry on, Professor, now. You can carry on now.
I can carry on. So this is better.
Yeah.
Okay.
Yes.
All right. So this was about our grand vision of M3I3. Now I'm going to narrow down my talk to the piezoelectric energy harvesting and show you how materials imaging can help design better performing energy harvester, particularly when we use ferroelectric materials. So let me move on to my paper that was published 6 years ago in Proceeding of National Academy of Science in the United States of America. So this was dubbed charge gradient microscopy, and it was in collaboration with Andrea Reloff, a good friend of mine who was a team leader at Seagate, Professor Yasuo Cho at University of Toku. He was the inventor of scanning nonlinear dielectric microscopy that was transferred to Seiko. Now Seiko was acquired by Hitachi. So you can see three of us worked on together on this charge gradient microscopy, where you can see the AFM tip is rubbing the surface like tribal, but it's not like tribal where the different materials in contact will align the Fermi level and have a charge transfer, which is really small, but the voltage is large. In this case, we are cutting the chemical bond mechanically, producing an equilibrium state instantaneously, and make the circuit compensate for this inequilibrium. So the current flow through the tip will replicate the domain structure underneath. So that was the idea behind this charge gradient microscopy. So in cartoon, you can understand piezoelectricity is really when you squeeze your polar materials, your polarization change most probably will decrease, and therefore the screening condition change, and any excess screening charge will be fired, will be laid off, and they will go through the circuit, which contributes to the piezoelectric energy harvesting current. And you can understand why the current is so small, because the delta Q is so small and rest of them stay there. So what if you can squeeze and let them out at the same time? Then you can see how you can increase the current in the circuit. So how do we prove it? Through materials imaging. So we have three modes here: piezo response force microscopy, which is shown here, electrostatic force microscopy, which is shown here, and charge gradient microscopy, which is shown here. If you look at into my book that I edited in 2004, when Sergei Kalinin was a graduate student with Professor Don Bonnell, he contributed a chapter where he calculated the surface potential variation of unscreened barium titanate, where the domain size is about 10 microns. And when we have fully screened barium titanate, and see how that contributes to the surface potential variation on top when we measure that with an AFM tip. And you can see that the surface potential difference between up and down domains when unscreened is about 80 volt, this is large, but if it is fully screened, it's less than 400 millivolts. So you can see orders of magnitude change just by having screening charge on top of your ferroelectric domains. And that's what happened here. You can see the periodically poled lithium niobate where you have up and down domains polled by the vendor. And you can see in PFM, the phase clearly shows that you have up and down lamella type of stripe domains. But if you do EFM amplitude, which is sensitive to the electric field, the straight electric field gradient square, then you see nothing. If of course, if you have very sensitive EFM, you should see something, but because the variation is so small, you see nothing, which means that it's fully screened. Now, in this case, when you do CGM, which is the case in C, where you're rubbing your tip and collecting the current out of your screening charge, then if you do EFM, you see clear contrast. Even the sensitivity is low, you can see clear contrast both in amplitude and phase, which means that has to be something done to the screening charge or polarization. And if you doubt the polarization, you do PFM again, and you see no difference. That means that has to do with the screening charge, which means we scrape the screening charge off of the surface. Now, can that come back to the same equilibrium state? Yes. And if you see this imaging of CGM and do EFM as a function of time, you see the contrast fade. So you can make a loop close from scrubbing the ions absorbed to the ferroelectric domains and then make current flow. And then from the ambient, you can have another screening charge falling on the top of the surface to make it happy again. So this is like mechanical energy translated to chemical and electrical energy. So you can see by just doing materials imaging, you can get some idea how to design another type of piezoelectric energy harvester. Now, with that, I hope that I convey my message that materials imaging at various scale can really contribute to expedite the innovation in energy harvesters, sensors, and actuators. And think about this. When we think about sensors and actuators and energy harvesters, in fact, they share common theme, right? We are transducing one type of energy to the other. We are transducing one type of energy to the other. For example, if it is sensor, right? For piezoelectric sensors, we are transducing mechanical energy into electrical energy, and actuators is vice versa. An energy harvester is close to sensor. It's just that in case of energy harvester, you don't need additional power source. While for sensors, you may need power source to amplify the signal that you're collecting. So you can see all of those can be brought into one basket. And when we design those, there are common parameters that we can deal with. Now, I'm going to give you one example. My student now, Dr. Ryu Jeongjae, who is now working for Samsung, did. So he came up with an idea to use the PVDF TRFE, which is the polymer ferroelectrics, to use it as a liquid volume sensor, okay? And here's the starting point here. So here's the thing. Students at KAIST bring tumblers. These days, the summer is hot. I don't know if it is hotter than India, I doubt, but it's pretty hot. It's like 35 degrees Celsius in hot summer days.
That's really hot.
Yes. So, and it's very humid. So students bring, bottles like the one shown there. And sometimes, if you put the bottle in the refrigerator and you want to know if I have to fill my bottle up, sometimes you just want to use a smartphone. And that's now being possible because now with this sensors and actuators, this is a smart way to know what the level of water is in the bottle. Of course, you may argue that that doesn't really help so much. But when you think about the fuel tank in cars, Of course, we have a well-known buoy type of liquid volume sensor, but this can also replace that with not too much of a hassle. So let me tell you what it is. It's like a wine glass experiment. So in the old days, if you rub the wine glass, there comes out a sound that is a function of how much liquid you have in the glass and the density of the liquid, right? And this is known for a long time, that you have a 1-2 mode of vibration of wine glass. And we found that this is relevant to our plastic bottle as well. So my student then came up with an idea that what if we have a piezoelectric sensor to catch the resonance, the mechanical resonance of the glass that is induced by impact. And this impact I will show you, can also be induced by actuator with the same material. And as you can see, the peak of the resonance shift as a function of the volume of the liquid. And if I do simulate that with the finite element model, we can really correctly predict, for example, how much water there is when we know the center frequency of the resonance, 1-2 mode. And you can see the red line is simulation and the black line is data. And you can see the error increases up to like 4.3%, but I think that's pretty good, right? So you can see this is something that we can use. Now, my students also wanted to make an integrated stacked actuators. So he integrated sensor and the actuators on top of the bottle and showed that this is really doable. And this is the slide that I'm showing you that is doable. Again, also he stacked multiple actuators to see it is like a superposition. It didn't work like that at the fourth layer, but I would say it was pretty close. So I was very happy with this first paper he published. So I'd like to summarize the first part of this small example, that we have demonstrated a flexible volume sensor based on PVDF film, and adding water up to like ½ liter to the liquid container created clear resonance frequency shift from 493.2 to 181 Hertz. And we deduced a function that can be used to relate our measured resonance frequency to liquid volume. So this is relationship. This is the relationship between the water volume. It could be also a structure parameter, right? The water volume with the resonance frequency of the whole structure. And we were successful in implementing a small patch of PVDF to quantitatively measure that value. All right, let me then move on to the second part, which is related to energy harvesting and sensor, okay? The first part was about sensors and actuators. Now the second part will be about energy harvester and the sensing. Again, the materials that we used is PVDF TRFE or PVDF, that is the polymer ferroelectrics, our favorite materials. And here, the same person came up with an idea to use the sharp pencil rod. Do you remember when I was a kid? That was a long time ago, like, let me say like 35 years ago, I guess. When I was a kid in middle school, I used sharp pencil with a rod type of carbon rod, and it was from Japan, mainly made in Japan. The diameter was 0.5 millimeter or 0.7 millimeter, and I see amazing that this technology has survived for like 30 to 40 years. My kids even used the same carbon rods, and he got an idea. If this is such a reproducible technology, why don't we use that as a template to make a blood vessel or vein, right? Vein type of harvester or sensors that could ultimately get interweaved to like the clothing or even like our skin or even inside under the skin. So that is what is this about, this intrinsically stretchable multifunctional fiber with energy harvesting and strain sensing capability. So I'm not going to bore you with these kind of introduction, but to recap, you know, if we can put functional devices to our clothing, we can do a lot of things. Of course, there might be some people who are against this because they want to separate the device with their clothing, but you know, who knows? The Fitbit or the Apple Watch or Samsung Galaxy Watch, now everybody seems to like it rather than the Rolex or the analog watches that was favorite of our old generation, right? And you can also see in the nature these kind of fiber type structure, which is very flexible and can be stretchable. So flexible or bendable and stretchable is different thing, right? You can bend things, but you may not be able to stretch. For example, you can fold the Galaxy folder, but you cannot stretch, right? It is not stretchable. So you have to separate them out. Now, with that in mind, you can see fiber-based sensor have been tried by many groups. I cannot cover all of them. However, if I may pick some examples, you can see them in this table. So there are fiber type strain sensor like CNT-based fiber, CNT-based cotton thread, PDOT, PSS, silver nanowire-based fiber, graphene-based fiber. Of course, they are not they are not exhaustive, but they can give you some glimpse, okay, idea what people are doing. And you can see the stretchability. You can also see the gauge factor, GF, varying gauge factor. And you can see we have a lot of room to improve, right? So as I told you, the template that we used to make this device was the carbon rod that we use for sharp pencil. So you can see in this SEM image, the scale bar is 1 millimeter. And you can see it's roughly 500 micrometer to 700 micrometer, the size of the hole. And if you blow up, if you magnify the image, you can see there's multiple layers, including PDMS, multi-wall CNT, PDOT, PSS for conducting layer, and PVDF TRFE with PDMS composite layer, and then again with the same materials in the reverse fashion. And you can see this original state, stretchable, bendable, and twistable here. Now, you can see the process flow here. So you can see it starts from carbon rod. This is really the sharp pencil that I mentioned, going PVP layer, PDMS, multi-wall CNT, and so on and so forth to make our final structure where you have hollow fiber, which is both bendable and stretchable. So here is the basic performance, as if you may, and you can see the output voltage. And when my finger tap on top of it, you can see a symmetric voltage there because pressing and releasing has different strain rate, as you can see in the magnified graph on the right side. And if I change the connection, you can see the same thing here, right? And also we can simulate them. So fiber is amazing in the sense that you can squeeze it to the extent that it's not possible with a bulk wire. And also you can see by reversing the connection, it is really there. It's not something like an artifact or like capacitive charging or discharging. And you can see depending on the rate of stretching and releasing, you will see the output voltage scales with the velocity. And to give you some number, when the strain rate was increased to 50 centimeter per second, the output voltage reached 0.9 voltage. So what about the durability? So 1,000 cycles is not enough. I know that. So here is our homework. To make this really something we could sell to the market, we need to come up with an idea how to accelerate these kind of durability tests, and we need to have a solid model to extrapolate the accelerated test to the normal environment test. We don't have the luxury to test for 10 years during the project time. Nevertheless, the people may want to know whether I can use it for 10 years or 5 years. And therefore, we need to have a solid theoretical backing as well as simulation work to make this more reliable. However, up to 1,000 cycles, you can see we had a pretty reliable result as shown in the slide. And here I will show you some video. I'm not sure if you can see it clear. I hope it will be shown. But you can see if we flow water through this small hole, it bulges. And when it bulges, you can see the fluctuation of the voltage, which means we can also use it as a flow meter or kind of a pulse flow detection for various purposes. Now, I'm going to move this onto strain sensor, right? So because we have this multi-wall CNT/P.PSS, it is stretchable. And because it is also composite materials of PDMS and PVDF, it is stretchable. So now we have one parameter to quantitatively assess the performance of the strain sensor, which is gauge factor. And you can see in the equation, it is defined by the ratio of the resistance change over the original resistance divided by the length change over the original length of our strain sensor. And when we do that, one thing that we found that we have small cracking occur in our morphology, which means maybe we have an issue with irreversible change of the resistance. But once we have the crack there, they don't propagate further and they stay there. And for some reason, they give us a pretty reliable gauge factor, which we can see here. So you can see up to like 1,000 cycles. You can see the change of resistance remains pretty constant. And again, this is not sufficient. We need to do more. And I know that. And in order for us to do that, as I mentioned before, we need a solid simulation and accelerated test behind this kind of assessment. So here, I hope that I convey the message that with a simple idea to use carbon rod as a template and the stretchable materials with the structure of a hollow fiber, we were able to come up with a stretchable in addition to flexible sensors as well as energy harvester, even though the output power was not very large, okay? So last but not least, let me introduce to you our third part, which is the fabric-based wearable piezoelectric energy harvester, and which was published this month, I think. So you can visit this Nano Energy website to see what we have done. Here, I will show you another introduction slide that you may already know. And you see this Soin et al., who published in Energy and Environmental Science in 2014. I was asked to comment on their paper in RSC. So I did comment on this, that this could be a innovative way to combine the pillows or garments with the functionality. That was 6 years ago. Now, the thing with the yarn or fiber that I have just shown you may be a little bit tricky than we think. So another way to do it and simplify the process is to think of like a panini type of thing, right? And this is all about this. So if you think about panini, bread, cheese, and ham or veggie in between, right? And do hot press, then we can do the same with PVDF, TRFE, polymer photoelectrics with, let's say, the nickel coated or copper coated or some type of conductor coated fabric. So if we have fabric, piezoelectric layer, fabric, and we just hot press them, that will be the simplest process we can think of. And I don't think I have to remind you of the physical properties of PVDF, but for those who are new to this field, I will just glimpse over the table on the left hand side where you can see the typical prototypical PZT has like 593 picocoulomb per Newton, which is pretty high as a D33. But if you compare that with PVDF TRFE, it has one order of magnitude smaller one, but still it's larger than zinc oxide or aluminum nitride. So you can see it's in between. And it is polymer. So you can think that this chain could be very flexible. Now for this one, the processing flow is shown here. And I think I started my talk at 2:40, right? And if I add 45 minutes, I got like 5 or 10 minutes. So I will make sure I don't speak more than I should. So here you can see we have solution preparation, we do tape casting, and then we do just hot pressing, and that's it. So you can see it's pretty simple. And you can see out of 8 samples, the thickness uniformity is impressive. In Korea, we have a lot of food that students can buy outside the campus, and that's a food truck. And there are like bungeoppang. Bungeoppang is like fish bread, but in fact, there's no fish in it. It is just fish shaped. And I tell people like my students who do processing or synthesis that you should do like them. When you make fish bread, it has to be the same size, it has to be the same taste, it has to be reproducible. So that's why I put this plot here. It seems to be very reproducible. And as you can see here, it has an interesting structure. It is like a Roman construction where you have pillars everywhere, which nails down the movement of your structure. But at the same time, it can also make sure that your structure is reliable. And the picture underneath is the simulated one from my colleague in the Department of Mechanical Engineering. And you can see the thickness of these PVDF TRFE. You can see how they are interweaved, and you can see how they are aligned. The lamellar structures is well preserved with alignment along a certain direction, which kind of guarantee high piezoelectric property. Now you can see more of the structure here, and you can see the overall structure depending on the hot press temperature, whether it's 110 degrees Celsius or whether it's 120 degrees Celsius. And you can see the melting temperature is about 150 degrees Celsius. So the closer you get, the messier the structure will be. So our best temperature was 110 degrees, as you can see, and the pressing pressure was 14.7 megapascal. And we also did chemical characterization using FTIR and the X-ray diffraction pattern. And you can see the 2 theta value of about 19.8 is the sweet spot for our beta phase, which is the ferroelectric beta phase. PVDF has alpha, beta, gamma, and delta, but beta has the largest piezoelectric property. And you can see for our anneal fabric based, the theta value is a bit smaller than the other, which means it's in tensile stress. And that is understandable because the nickel or the metal electrodes will shrink faster than the PVDF when we quench it. So you tend to have a tensile stress. Oh, maybe I'm wrong. Let me take that back. So I will think more about why we have tensile stress here, okay? And then we did the simulation and also tried to calculate the piezoelectric potential variation as a function of the concave and convex structure in our fabric, and came up with the number that is close to our experimental value. I'm not going into detail of this stress boundary condition or voltage boundary condition. Anyone who is interested can read the supplementary information, but even after reading that, if you don't understand, please email me. And we did the standard testing of the pressing and bending, as you can see, and you can see the voltage output is pretty reproducible. And also you can see forward and reverse connection to see if there's any artifacts involved in our measurement. And also, due to the reviewer's request, we did capacitor charging. In this case, it was 1 microfarad with the bridge circuit there. And you can see the full charging happened at about 140 seconds. And you can see when we changed the load resistance to optimize the maximum power density, it was about 60 mega ohm load resistance that did the work. And also we did 15,000 cycles of 2 Hz periodic bending to see if it is durable. But again, this is not sufficient. I think the same message here, we need to do better in the durability assessment. And the other part we did was because if I have a clothing and if they're peeled off, right? We have a lot of hot press garment where you have logo of many things, but if we wash that clothing, we see a lot of peeling. So we don't like that. So we wanted to characterize the peeling strength, the adhesion strength between the fabric and PVDF TRFE. And lo and behold, the adhesion strength was 22 Newton per centimeter, which is the largest or highest that I've seen before. And to give you a perspective, PVDF is the binder used in lithium-ion battery. And if I talk to battery people, they don't know PVDF is ferroelectric. They just think it's chemically inert binder. So we need to talk. We need to talk to other people in other fields, right? But then in their case, the binder is to adhere the particles of the active materials in battery. They have 1/5 of the adhesion strength that is lower reported than here. So you can see how strong the binding is between the PVDF layer and the fabric. Now people ask, if I do 15,000 cycles of bending, will the adhesion change? Yes, and you can see adhesion after bending test even increased. So if you do statistical analysis, you can say that this change is meaningless to the confidence we have. So we can say there's no difference. And you can see other references that shows you some of the adhesion strengths for different materials. So you can have a feel how 22.0 is large. So with that, I'd like to summarize my third part of my talk by saying that we have now a recipe to make panini type of fabric-based energy harvester, and it is really durable. And the thing we have to do is to increase the output performance of the energy harvester. So with that, I hope you enjoyed my talk, and I'm going to stop here.
Okay. Thank you, Professor, for an interesting talk. In spite of the bandwidth problem or the screen issues, but still we enjoyed your talk, and most of the slides I can understand. And for example, let me identify the slide number. 2830, you are showing some slides of the piezoelectric sensor measurements, where we also focus on the peak-to-peak voltage as a function of frequency or applied load. So those slides are very familiar to us. Just to say a few words about our case, like though we focus only on the ferroelectric crystalline phase changes in PVDF and PVDF TRFE, when I was doing my postdoc in Gyeonggi-dae, if you have been knowing Professor Kabjin Kim, he's a meter scientist now. Now Professor Hongdo Kim is there. He also presented yesterday. So our research is somewhat overlapping in the sense, like we are studying the crystalline phase changes, and then we go for electrospinning, and then we do the measurements. But in your case, you divided your talk into 3 different parts. The good thing we like is you also acknowledge your students' role there. You put the pictures and you talked about them. I want to mention about your website actually to the audience here. Those who want to see actually how a research group can do a good work and how the guide actually treat the students, you better visit the professor's homepage. You can see over there like how they work very hard, and also have a weekend get together, and also distribute some competition kind of prizes, awards, in order to encourage the students to work with. Actually, I just want to say this because like the main, the aim of this conference is to create awareness and spread information about research, good research. I also want to mention about your Coursera. Like you have made a course in the electrodynamics introduction where we registered. I also requested you to make a course, actually, probably you may not have time for that, on piezoelectric sensors, like whatever you have the slides here in the way of a MOOC course. And probably if you make that, I'll be your first student. And,
Thank you.
I'll just read out 1 or 2 questions, which is actually raised by Professor R. Vijayaraghavan, a senior professor in our school department. He asked actually, what is the best piezoelectric material used in your lab in terms of coefficient? Actually, you showed in the table. So can we say like PVDF and PVDF TRFE is a material you used till now in your lab?
Yes, so here are my favorite list of materials. For polymer ferroelectrics, I like PVDF, TRFE.
Yes.
For ceramics, I like PMNPT, PCT, BFO, and barium titanate.
So you can
those
see
are
on the screen. Yeah, you can see on the screen of Professor Vijayaraghavan.
Thank you. But what about the composites? Are there composites enhancing this?
so we are
Composites
also looking into composite, but because composite materials is not my strength, we are collaborating with other people on that, like having so one thing that I didn't understand was having PVDF and barium titanate as a composite, because they have opposite polarity of D33. So we need to then have a structural design to make sure that they don't cancel out each other. But yes, I'm also working with truss structure. So now we will soon publish zinc oxide truss, where you can see the hollow fiber type of truss can have an excellent mechanical property as well as piezoelectric property. So we are slowly moving into that territory. But as we move the territory, we see the boundary becomes very large. So it's hard to focus on one thing. So we don't want to expand our boundary too much, but still, yes, we are talking
It's the scope, I thought. Is the scope, or I know not your research, but is there a scope of composites exploration?
Yes.
Thank you.
Thank you.
Let me continue here. So when we are working still with PDF and TRFE for the past 10, 15 years, in our case also we used to work actually. Then in our lab, we moved on to the PLA. It's a biodegradable material. So when I asked my professor about its advantage, he talked about its peak-to-peak voltage is still lower than PVDF, but it has a orientation, all-round orientation, 360-degree orientation. Unlike PVDF TRFE, where it will get cancelled out, the orientation, if you do it in the other way. If the polarization is opposite, they can get cancelled out. If it is in the same direction, get couple added up. But PLA don't have the issue because it has a cyclic orientation. Cost is cheaper. Have you ever thought about moving to biodegradable material, thermoelectric material?
Yes and no. As I told you, the front is becoming too large.
Yes.
So that part, I'm just following the other researchers group.
Yes. So you will stay with the TRFE PVDF.
Yes.
So Professor, we learned a lot of new things in your presentation regarding the imaging technique and the non-contact flexible volume sensor. But the other last few slides we were able to understand. And if any more questions, I can share your email ID to the participants so that they can post you. And please have your time to reply them. Thank you, Professor, for your presentation. Thank you so much.
My pleasure. Yeah.
Thank you.
Thank you very much.
Okay, Professor. Bye. So I pass on to the coordinator.
On behalf of organizing committee, I express my sincere thanks to Dr. Selvam for joining us and sharing his research work. Since we are running late, let us continue with a break. I welcome Professor Joost Rieck from University of Amsterdam, our next speaker. I invite Dr. Charles and Dr. Senthil Kumar to take over the proceedings of this session.
Good morning. Is it clear? Audible? Good to see you, Professor.
Yes, continue.
So here we are conducting the international conference now in Zoom and YouTube. We are almost 350 participants. So we are hearing from your excellent talk. And I would like to introduce some school deans, Professor Professor Vijayaraghavan and the Research Center, Dr. Senthil Kumar, also our organizing secretary, Dr. Cheralathan sir. So the second time I would like to introduce to Professor Senthil Kumar. Thank you, sir.
Yes. Thank you very much. I welcome Professor Joost Rieck for this conference. Before his talk, I would like to introduce his career. Professor Rieck completed his PhD in 1996 from University of Nijmegen, Netherlands. After that, he did a one-year postdoc with MJ Crossley, Sydney, In 1998, he joined as a lecturer in the University of Amsterdam. Following that, he was promoted as a senior lecturer, full professor in 2006. He also launched a InCAD company in 2009. He also involved in other research activities. In 2017, he is promoted as a distinguished faculty professor. He has received several honors for his critics. So I'm reading some of his honors. He is an honorary member of Israel Chemical Society in 2018. And is a young member of Royal Netherlands Academy of Science and Arts and Science, and a member of Board European Journal of Inorganic Chemistry, and the NWO, KNCE, and the Royal Netherlands Chemical Society, etc. He has received numerous grants of tuning of 13 million euros. He was invited for several invited talks in different countries in Swiss, France, China, Japan, and United States. He has guided 22 PhD. Currently, he is holding 22 PhD students and 9 postdocs. He has completed 48 PhD students so far, having the publication of total 300 over, H-index of huge 71. He has been recognized as a top 1,000 most cited scientist in the world at the age of 43. With this highlight, I welcome Professor Rick to deliver his lecture. Professor, welcome.
Yeah, thank you very much for your kind introduction. It's an honor and a pleasure to give a talk like this. Obviously,
Professor, I restrict your talk to 35 minutes, please.
Yeah, I will do my best.
Thanks.
So, yes. Can you see my screen?
Yes, it's audible. I think make it full screen, Professor.
Yes, yes.
Oh, that's fine. Is everything okay?
Good, good. So today I will talk about supramolecular approaches in the development of artificial photosynthesis. First of all, Charles asked me to explain some of our concepts in a little bit more detail because of the educational aspects. So what do I mean with supramolecular approaches? Well, here you see an example where we use program molecules. So here a phosphine pyridine and a zinc porphyrin, that if you mix them in solution, they self-assemble into a cage-type construct. And if you then add rhodium, you have a rhodium encapsulated in a specific environment. And we use these type of assemblies to control catalysis in confined spaces, giving special reactivity and special selectivity. And we have a plethora of these type of concepts and structures explored over the years. But today I will focus on solar fuels. And solar fuel applications are very important because we have to transform our society to sustainable energy. Of course, we have solar and wind energy, but these are intermittent. And this means that we need to store our energy, our electricity, and you can do that with solar-to-fuel technology where you create directly fuel, and for that you need catalysis. So if you think about storage of energy, then you can look at the table of energy density per kilogram, and then immediately you see that fuels are very energy dense if you compare them to other ways of storing energy. And this means that fuels are very efficient for mobile applications. For example, planes I think it's very unlikely that for the next 40, 50 years, we're going to fly with solar panels. So this will really need fuels as an application. And if you look at the current use of energy, then this is the worldwide consumption of energy. Then you see that more than 80% is in the form of fuel, meaning that it's very likely that fuel will be a dominant way of energy for the next, I think, 50 years at least. And for that reason, it would be good to generate this energy using solar. So this is already possible, and the most simple way of generating fuel from energy is hydrolysis, so splitting water into oxygen and hydrogen. You can use solar panels and then put them on the grid, and then if you have excess of energy that you cannot use at any time, then do a hydrolysis reaction to form hydrogen. So this is current technology that's scaled up. Efficiencies are around 10%. You can also do it in an integrated way. So here you see a solar device connected to electrolysis on site, so they are directly connected. But you can also make a really integrated system, a photoelectrochemical cell, where both the light absorbing event as the catalytic event are taking place in aqueous phase. And whereas these type of technologies are at the scale-up phase, these other technologies are still in the research phase, also with the idea, the aim to get much higher efficiency on the long term. So if you look at solar fuels, a techno-economic analysis that has been done by Remco Detz from our group together with TNO, then this is the cost price of hydrogen extracted from fossil fuels currently. And this is the cost price of hydrogen generated from PEM cells or from solid oxoelectrodes. So electrolysis. And then you see that we are only a factor of 3 away from being economic competitive. And if you extrapolate this, then by 2040 or maybe slightly earlier, then we can generate hydrogen from solar in an economic competitive fashion. So here you see a few early devices that are based on inorganic materials. So a solar cell connected to catalyst coatings to do on one hand, for example, water oxidation, and on the other hand, proton reduction. So these type of cells have been developed, and the efficiency vary a little bit between the 2-3% to up to 15 or 10%. But our group, we are we like to be inspired by nature, and in nature all these processes are well organized. So here you see a schematic picture of a leaf where light absorption takes place, where electrons are extracted from water. These electrons are carried away to photosystem 1, and here you get another energy injection via light, and here NADP is converted in NADPH, so the molecular hydrogen form of nature. And whereas the overall efficiency is not so high, the individual processes in nature are very, very efficient, and you can use them as a source of inspiration. And if you translate this into a synthetic system, then you generate a solar fuel device based on molecular components. So you need a photosensitizer, a linker, a water oxidation catalyst to convert water into oxygen, protons, and electrons. And on the other electrode, you need a photosensitizer and a proton reduction catalyst to reduce protons to hydrogen. That should be well connected via a wire and via a proton exchange membrane. And here I show you an example from the Sun Group where he uses a ruthenium dye to absorb the light and a ruthenium complex to do water oxidation catalysis, another ruthenium dye for light absorption, and a cobalt complex for proton reduction catalysis. And this is a standalone device that produces hydrogen and oxygen when you shine light on it. And in a second example, again, a ruthenium catalyst and now a organic dye are co-immobilized on titanium dioxide, and on nickel oxide, the other electrode, cobalt again, and again, a organic dye. So these are proof of principles, but the efficiencies and durability are still very, very low. Right? So efficiencies below 1%. So what I would like to do today is to show you some supramolecular approaches to improve these type of efficiencies by reducing charge recombination, reduce overpotential for production, proto-reduction catalysis, and optimize catalysts for water oxidation catalysis that proceed via dinuclear pathways. So, so if you look at, let's say, reducing charge recombination, then we should zoom in a little bit into how dye-sensitized solar cell works. So this is Michael Gracel. He invented dye-sensitized solar cell, where he immobilized ruthenium dyes onto titanium dioxide. And the energetic scheme is like this. So this is the conduction band of titanium dioxide. This is the band gap of the ruthenium dye, so the HOMO-LUMO gap. If you photo-excite the chromophore, then the energy of the electron is sufficient to be injected in the titanium dioxide, and then it can go to the counter electrode, and you have a redox mediator, redox couple for charge transport within the device. And currently, maximum efficiency is around 50%. And you have to realize that these dye-sensitized solar cells are very similar in principle to dye-sensitized photoelectrochemical cells. So here you see again a schematic picture of a dye-sensitized solar cell, where the dye injects electrons in the semiconductor, and you have this redox couple for shifting the charges. And this is a schematic picture of a dye-sensitized photoelectrochemical cell. You have the same type of dye on both sides, but instead of a redox couple, you have redox reactions, namely water oxidation and proton reduction. So this means that all the problems that you encounter in dye-sensitized solar cells, you will also have to solve for dye-sensitized photoelectrochemical cells. And if you zoom into this, so what happens? So again, so the green arrows indicate the favorable processes. So you get photoexcitation, and the excited dye injects electrons in the conduction band of the titanium dioxide, and then the electrons should move like this. But a non-productive pathway are charge recombination from the electrons from the conduction band to the oxidized dye, or to the redox mediator, or you get just a non-emittive recombination. So this is N-type, where you have electron injection into the conduction band. P-type, the other electrode, usually is using nickel oxide. You have very similar processes, but then the electron goes to the redox couple, and you have electron injection into the dye from the semiconductor, or hole injection into the valence band, if you like. So, so if you look at these charge recombination processes, they reduce the efficiency quite dramatically. And this is especially the case for P-type, because hole transport in nickel oxide is slow, meaning that you have more time for charge recombination, and as a result, the efficiencies of P-type dye-sensitized solar cells are quite low. So we thought maybe we can use supramolecular strategies to pre-organize the dye and the redox mediator, preventing to some extent this charge recombination, and as a result, the efficiency should be high. So we looked into the literature and found this paper by Stoddard, where he has this pseudo-rhodexane. So based on interactions between this charged ring and this electron-rich naphthalene ring, you can form in solution these type of pseudo-rhodexanes, where this ring is inserted, or where this thread is inserted into this ring. And the redox properties of this Viologen analog are ideal for redox mediating. So we thought maybe we can convert this P1 dye that had been reported by Sun into a PN dye that contains these threads, and these threads can then bind or pre-organize these redox mediator when attached to a surface. So we generated this, and then the overall dye schematic picture of the device should look like this, that we have this PN dye that has these threads, and then the ring can pre-organize for electron transfer to the redox mediator. And as soon as the ring is reduced, it will slide off this thread, and then it can be replaced by a uncharged redox mediator. And by doing so, you actively separate, let's say, the reduced redox mediator from the surface, thereby reducing charge recombination. And we constructed this material also a little bit in the presence of excess of this viologen. So we didn't need to use an excess of this ring for various reasons. And then the reduced ring can again in turn reduce the viologen that can further transport the charges to the other electrode. So how do we make these dye-sensitized solar cells? Well, we have a conducting glass slide with nickel oxide coated on that. We absorb our dye that has an anchoring group. We put the polymer spacers onto this, and then the other electrode is platinum spin-coated material with 2 holes, and then we seal and we fill it, and then we get, let's say, solar cells like this that are quite small initially, but just for testing. We made 4 different analogs. So these are all the control experiments, and this is the combination where we have our dye and thread, where the ring can go onto the thread, so with the pre-organization, and these are the 4 control experiments. And if you look at the results, so these are the photovoltaic performances, so these are the currents when we shine light on this. There you can see here that if you pre-organize our redox mediator to the dye, then we have about 10 times more photocurrent as a result of reduced charge recombination. So here we really show that you can supramolecular strategies to reduce charge recombination. And in a second approach, we used a different ring that is not charged in itself. And here you can see that we further improved our photocurrent by this pre-organization effect by using different rings. So in the second part, I will discuss how we can use supramolecular cages to reduce overpotential for proto-reduction catalysis. So here you see a few reported nickel, molybdenum, and cobalt complexes that have been used for proto-reduction catalysis. And what we need from these catalysts that they are stable, very active, and show low overpotential. And why is low overpotential important? So again, I will show you here a schematic picture of our intended device at the end of the day, where we have water oxidation here, proto-reduction there. And these are the energetic levels of the different components. So we have photo-excitation, injection, and then we have oxidation of our water oxidation catalyst, and then we can oxidize water to form oxygen, and on the other side, we can reduce protons to form molecular hydrogen. And here you see the overpotential. And the higher the overpotential, the larger the losses are in this device, meaning that the energy is converted into heat instead of fuel. And for that reason is that the lower the overpotential at which these catalysts operate, the higher the potential efficiencies of the eventual device. How can you measure this? Well, you can measure these by electrochemistry. So this is a schematic picture of an electrochemical setup where you vary the potential between the reference electrode and the working electrode. And at the working electrode, so here you scan, you increase the potential, and at some point you get a oxidation. So here we have an oxidation wave in oxidizing this organic compound. And if we then go back in potential, we get a re-reduction from this oxidized compound to here. So this is a simple oxidation. And here we do a similar electrochemical experiment, but then in presence of protons. So in this solvent now we have a proton reduction catalyst. So you see the first reduction wave that is nicely reversible. And then in the presence of increasing amount of protons, of acid, you see a higher current, and this higher current represents electrocatalytic proton reduction. So this is really a catalytic wave, and which is clear because the current is much higher than the current for just the catalyst. So what do we mean with overpotential? Well, here again you see a catalytic wave, and here you see a non-catalytic wave. So the catalytic wave is much higher than a non-catalytic wave, and so this is a plateau current. This is halfway potential. And imagine that you have a certain reaction with a thermodynamic equilibrium potential that is here. Then this is the onset potential. So this is the overpotential that the catalyst needs to drive this particular reaction. So it should be closer to here to get a more efficient reaction. And from these type of curves, if you do these experiments right next to this overpotential, you can also determine the reaction rate of the catalyst in solution. But this may be a little bit detailed. Okay, so what type of catalyst do we have? Well, we like to be inspired by nature, and if you look at nature, then you see these hydrogenase, and hydrogenase can do this proton reduction with no overpotential at 9,000 mole per second. So these are very, very fast and very, very efficient, and they have these di-iron disulfur cores. As a result, there are many people in the world that look at these type of complexes and make mimics of that. So these are some players in the field, and what these complexes all have in common is that they all need quite a large overpotential, although they are can be quite active. And generally, they are not as stable as the hydrogenase itself. So these are some of the mimics that we have made over the years. So also we are very active in this field. And also in our case, all the complexes need still overpotential. And if you look in literature, there was one interesting paper by Lubitz and Ryerson, and they looked at the APO system, the active hydrogenase, where they removed the active site, the natural active site, implemented synthetic analogs, and they report that full activity is restored, indicating that the second coordination sphere around this active site is of crucial importance. So we thought maybe we can mimic this by creating cages around synthetic mimics. And so here you see the natural system with the active site. We make mimics of that, and we want to put it in cages to create a sort of second coordination sphere. And we wanted to learn what the effect is of this second coordination sphere. So we made Nitschke tape cages based on this unit. And if you make these type of zinc porphyrins with this ditopic ligand, you add iron, then by a self-assembly process, you form these type of molecular cages with 6 of these zinc porphyrins. So you can measure these compounds. So these are the mass spec, high resolution mass spec analysis, and these are the modeling structures where you see nicely these zinc porphyrins forming a molecular cage. And if to this cage you add this di-iron complex, which is a hydrogenase mimic that is functionalized with a phosphine trispyridine, then the pyridines, they coordinate to these zinc porphyrins, and as a result, it binds into this cage. So this is a modeling structure of this hydrogenase mimic in a cage, and also this can be fully characterized by mass spec, DOSI, and UV vis tabulations. And if you then look at the effect of encapsulation on proton reduction catalysis, then you see these results here. So first we look at only the hydrogenase mimic. If you look at only the reduction and the reoxidation wave, you see that the reaction is not completely reversible. So this is scan rate dependent. And if you look at the current as function of the of the scan speed, then this is the reduction and this is the reoxidation. And when it is fully reversible, you should get this line, and we have discrepancy between that, indicating that we have some decomposition. And if you do electrochemistry and IR, in situ IR, then you can monitor the IR frequency of these COs that are coordinated to this. And from this, we learn that upon reduction, we get disproportionation into a bisphosphine complex and the hexacarbonyl complex. And that we see from the IR frequency. So we have disproportionation indicating that this monoreduced form is not stable. But if we encapsulate this hydrogenase mimic, then we see that this disproportionation no longer occurs because these compounds are isolated in this cage, indicating that they cannot do a bimolecular reaction. So this is the first win, the complex is more stable. And if we then look at electrocatalysis, so in the presence of acid, so here we see the reduction wave, the catalytic reduction to form hydrogen when we just use the mimic. And here we see the catalytic wave when the catalyst is mounted into this cage, and we see a shift of 155 millivolts to more favorable potential. And this means that by encapsulating these hydrogen mimics, we can reduce the overpotential at which this catalyst is doing proton reduction catalysis. And this is also clear from the tafel plot that is shown here, where we have the activity plotted as function of the overpotential. And here you see that when encapsulated, you reach the maximum rate, but at lower overpotential, but still 600 millivolts. Next, we thought, can we also create multi-complex systems in larger nanostructures, and can we create a more controlled environment around these hydrogenase mimics? And in order to study these systems, we looked at M12L24 self-assembled spheres. And this work is initiated, or let's say the self-assembled spheres are developed by the Fujita group from Tokyo, and they used many different ditopic pyridine building blocks with different functionalities at the endo position. And if you add palladium or platinum precursors to this, these type of structures self-assemble by just mixing these components in these constructs that contain 12 metal centers and 24 of these ligand building blocks. And you can put any functionality here you like, more or less, even peptides, as Charles knows. So we did this also. So we made this hydrogenase mimic attached to this ditopic building block. And if we mix in a palladium precursor, a other ditopic ligand, then we can make, on average, a nano cage that contains 12 metal centers and 24 building blocks, of which about 5 or 6 of these hydrogenase mimics, and the rest are not functionalized. We can also mix in, let's say, this ammonium salt, and this is, in fact, the acid that you want to reduce. So you pre-organize the substrate that you want to reduce with the catalyst in this nanosphere. And we characterize these systems completely, including with DOSI. And then we can study the effect of encapsulation, and we can study the effect of encapsulation and pre-organization of the substrate that you want to reduce. So here you can see the electrograms where we have pre-organized the acid substrate and the catalyst in the cage. So I will explain the electrograms. So in red, you see just the building block in absence of acid. So we have a reduction wave here. And then in blue, or in black, we see just the building block in presence of acid. So we see here the catalytic wave for proton reduction. And in blue, we see the electrogram of the cage. And here we see even in absence of external acid, we see already a catalytic wave, meaning that these protons that we pre-organize are already reduced, and importantly at much lower potential. And if to this case we add additional acid, then we see that the blue wave is increasing in intensity, indicating that also the external acid that we add to the solution can be transported to internal and can be converted electrochemically to form molecular hydrogen. And the key point is that the overpotential at which proto-reduction takes place is much lower by this encapsulation effect. And if we now compare in a tafel plot all the three approaches, then we have here, we had our single site that was already reducing protons at lower potential compared to the free one. Here we have the black line is the free building block. So it has a higher, it has a relatively high rate, but at high overpotential. If we encapsulate without pre-organization of protons, we see a shift in potential, meaning that at lower overpotential, we have proto-reduction catalysis, but also at substantial lower rate. But if we then pre-organize protons also in the same case, then we do proto-reduction still at low overpotential, but again at much higher reaction rates. So by controlling this environment, we can control this overpotential. And in the last few slides, I would like to show you that next to proto-reduction, we can also optimize catalysts for water oxidation using cages. So here you see some of the complexes that are studied in water oxidation catalysis. So iridium complexes are quite good, and also ruthenium complexes are doing quite well. And I think this is the best catalyst that has been developed by the Sun Group. And for that reason, we also looked at ruthenium catalyzed water oxidation. And interestingly, we observed a big difference between this ruthenium complex that is based on this BP compared to this complex that is based on the phenanthroline. So a very small difference, but a big difference in pathway. So what is the mechanism? Well, you do proton-coupled electron transfer from ruthenium 2 to ruthenium 3 to ruthenium 4,5. And then from here, there are two different pathways. Either water is nucleophiling, is attacking the oxo species to form this peroxo. And then you, after further proton-coupled electron transfer, you form oxygen, protons, and electrons. Or the other mechanism is that two of these radical oxo species, they react in a dinuclear mechanism to form this oxygen-oxygen bond in one step. And this follows the dinuclear pathway, and this follows the mononuclear pathway. And that's also clear from experiments done by the Sun Group, where here you see an X-ray structure where the oxygen-oxygen bond can be formed, because in this X-ray structure, they can approach sufficiently close to form this oxygen bond. But it was an interesting paper by Meyer et al. They did kinetic isotope effects, and they found that under very dilute conditions, the oxygen-oxygen bond cannot be formed because these complexes cannot find each other very quickly. And as a result, he found first order under these dilute conditions as determined by isotope labeling. So the question is, what is the real mechanism, and can we control the activity by facilitating this dinuclear pathway? So we made some analogs of this ruthenium complex that contain pyridine sulfonates for both the BP and the phenanthroline analog. And we used our nano cage that contains 12 metals and 24 of these cunidinium binding sites, and they can bind to these sulfonates. So in both cases, we demonstrated we can upload up to 12 of these complexes inside these cages, leading to very high local concentrations of catalyst. So about half a molar of catalyst inside, which is extremely high. So next we studied the effect of this local concentration on this ruthenium catalyst. And here you see the electrocatalytic current as function of the gauge concentration. And in all these reactions, the overall catalyst concentration is low, like 10 to the minus 5. And by only changing the gauge concentration, we can change the local concentration of ruthenium catalyst within the gauge. And in the situation where the local concentration is highest, we have the highest currents in these experiments. So we can use this also to extract the relative rates. And here in this plot, we see the relative reaction rates compared to the free complex as function of the local concentration. And you see here, if we use this ruthenium complex that operates via a dinuclear mechanism, where two of these ruthenium complexes need to find each other, we see a huge increase in reaction rate as function of the local concentration, whereas in contrast, this complex that reacts via a mononuclear pathway doesn't show any effect upon concentrating in this nanosphere. So clearly we can facilitate by supramolecular preionization this dinuclear pathway, and we can increase reaction rates by a factor of 130. We also looked at the kinetic isotope effect, and we see also that the kinetic isotope effect is changing as function of the local concentration. And from these kinetic isotope effects, we know that the pathway of this complex is going via this dinuclear mechanism. But at some point, the local concentration is so high that also the preceding proton-coupled electron transfer becomes part of the rate equation. And as such, we see the kinetic isotope effect also increasing as function of the local concentration. So with this, I hope in time that I have shown that supramolecular strategies can contribute to solve challenging issues that we need to solve to develop dye-sensitized photoelectric chemical cells that run with high efficiency. So we can reduce charge recombination, and we can control catalyst properties by organizing molecular components in the proper way. So this is just a start, and so I think over the next decades we need to develop more of these strategies to really arrive at efficient devices. With that, I would like to thank the group. So these are the current students that are working on this project. I would like to thank Simon Matthew, who is an important key player, and also Remco Detz, who has been supportive over the years. He's now working at TNO. And these are the former members that worked on this project. I would like to thank funding, and I'd like to thank you for your kind attention. And if you have any questions, then I would like to answer.
Professor, it's a very interesting talk. You have covered so many wealthy information. I feel this is truly interdisciplinary area covering material science, inorganic chemistry, complexes, electrochemistry, and the photoelectrochemical system, and so on. So many fields you put together and presented as a cross-disciplinary area. Wonderful presentation, Professor. Professor, there's a few questions. Actually, first you have presented that the photoelectrochemical system using this macromolecular systems. And what is the scope for the upgrading this kind of photoelectrochemical system, large scale electricity production? Do you have, please, I welcome your comments on this.
So your question is if we can scale up already this?
Yes, yes.
Yeah, so that's a good question. So, so this first device we made was clearly a proof of principle. So these microcycles, we cannot prepare, I think, at large scale. Okay. But we are currently making, so we are fine-tuning the building blocks.
Okay, okay.
To have advantages in pre-organization and combine that with, let's say, synthetic accessibility.
Okay.
So, and that should be scalable at, in the long term. Yeah.
Okay. Professor, some audience now would like to know what the stability of this ruthenium complex under this photochemical and conditions.
Yeah, that's a very good question. Thank you for the question. So the ruthenium complexes underwater oxidation catalysis are quite stable. So these ruthenium complexes were chosen because they represent the best catalysts, homogeneous catalysts so far, and the ruthenium complexes themselves can reach about 1 million turnover numbers. We also looked at the cages, and also the cages, they are stable under electrocatalytic water oxidation conditions. So we analyzed the compounds after bulk electrolysis, and they were still intact.
And two more questions, Professor. Professor, I could see now in your systems, you have used some of the chemical compounds like acetonitrile, pyridine, but the environmental point of view, you think this kind of systems is extendable to futuristic energy productions?
Yeah, that's also that's a good question. So if you look at dye-sensitized solar cells, they also contain these type of solvents. And the question, well, I think they need to be further developed to take into account all aspects, including, let's say, sustainability aspects for preparation of these type of compounds. So this is really a very early stage, I would say, rather conceptual to understand which parameters we should look at to improve efficiencies.
So there's a last, I think this is a feedback, not a question, is a feedback. I could see, in one of your slides, the complex iron carbon monoxide pyridine complex used for a hydrogen evolution reaction. You have showed one cyclic photometry graph, and within that, you made a plot of peak current versus scan rate.
Yes.
This is just feedback, because since it's a diffusion control system, why not use peak current versus square root of scan rate? Because Randall-Sevik equation is one of the standard equation used for this kind of benchmarking system. You should use root of scan rate versus IPA or IPC. That is the right way of making the plot.
Yeah, you can do both. Yeah. So you can do both.
But if you use scan rate, that means the systems involve surface confined system. But that means if you mount the redox couple on the electrode surface, then you can use it the equation of IPA, IPC divided by versus the scan rate. No, just as a feedback.
Yeah, I know the feedback. Yeah, so the person that wants to give that gave the feedback can contact me, because I can explain in more detail. Because this is a variant on this. This is a variant. I'm completely aware of this. So because we didn't plot the peak current, but the deconvolution of that. So the
peak current versus square root of scan rate. That's a diffusion control system, because you are taking your complex in the solution. So it is a diffusion control system. Electrochemical reaction involves with the diffusion control system. It follows a Randall-Sevik equation of IPA or IPC directly proportional to V of.
Yeah, so, but it depends on what you put on the y-axis. Yes.
Y-axis is the current. That's a peak current.
And we didn't put the current on the y-axis, but the derivative of that.
Okay.
So we talk about the same. We just have a slightly different plot of it. But
okay, Professor. With this now, I thank Professor Rick for a wonderful presentation and for the interaction. Maybe future, if any chance, we also welcome to Vellore Institute of Technology for some collaboration. We'll look for you, sir.
Yeah, and if people have any final questions, they can always contact me by email or something.
Thank you very much. Kind support. So I'm handovering to the organizer.
Hello. Yes, thank you very much, sir, for your interesting talk. I look forward to meet you in the campus. I think because of this situation, we are not able to have this conference in the offline mode. So thank you so much for the interest shown and for accepting our invitation. And I would like to request you to visit our campus in future when the situation is all right. Thank you so much, sir.
On behalf of organizing committee, I sincerely thank Professor Jose Freak for joining us and sharing his research work. Now we break for lunch. Let us join at 2 p.m. for the post-lunch session. Thank you.